Taking it from the source, this is about integrated security. We're using the LLVM tool chain, okay? We're talking about static and dynamic, linking them together with LLVM tools. So if you want to leave the room, now's the time. Go ahead. This is funded by DARPA. This is a research project funded by the Cyber Fast Track. For those of you who haven't heard about Cyber Fast Track, DARPA's made a lot of changes in the last year and a half, 2 years, trying to get involved with hackers. Individuals, very small groups, giving them a small amount of money in a short, relatively short amount of time, and then saying, okay, prove me you can do something interesting, and we'll take it back. They are primarily interested in defense. Offense is usually classified. So I got some money, and this is some of the work I'll be presenting. You'll all be calm to know that I am not from the government. This is my disclaimer. The other issue from DARPA is I have to go through a public release cycle. Okay, so the slides here are about 3 weeks old compared to the actual work that's going on. This is an ongoing project. So approved for public release. If you want the slides, you can have them. Otherwise, I have to hold back till everything's done. All right, so the goal here was to build a tool that allows anybody, whether developing software, to start actually looking at security aspects as they're developing rather than after the fact. Okay, when you do it after the fact, you don't build security in, there are consequences. Okay? It's also one of those things about education. I've talked to a lot of folks, both in this conference, other places. You go, people who talk about their mistakes they make. You learn from your mistakes. Okay? Getting somebody where you have an integer overflow and the next day someone popped root, that's an interesting phone call coming from outside the company versus inside the company. Okay? You prefer it to come inside from people you know. And you tend to learn from those things. The other thing about LLVM that was really particularly interesting in terms of the goals was, it's open source community. You can have a lot of tools. There are bindings for both C++, Python. Python is, as was mentioned in the high performance computing, it's very interesting for high performance computing, also for hacking. Love, great language for hacking. So the subtitle for this slide probably could be is how I got money from the government to do something I wanted to do anyway. So if you're interested in that, this is the kind of thing. I basically pitched to them, look, you can build tools from LLVM, put it into a development environment, start getting some information about security, and that'll make code more secure. You can allow it for sharing, better educated, better secure, better code. So in terms of what I'm looking at, a little tall. Static analysis, it's already built in. We already have it. Okay? Call function graph's already there. Data dependency, that I have to build. A hypothesis engine, I have to build that. Fuzzer, I can already kind of build that from scratch at the beginning as well. Okay? Start looking into these static analysis. So I basically rewrote the CCC analyzer scripts from Perl to Python. Okay, it was not a pleasant task to do, but it's something that had to be done because I wanted something to all work in one language. Plugins, callback, go back, reiterate on the static analysis. Okay. I did not want to do HTML as much. I prefer it to be a little lightweight, pass things back and forth. So JSON, you could save it to SQLite, any of those kind of formats, that would be preferable as well. Reuse the infrastructure. I mean, I'm happy to take what's already there. Most of the code that's being tested right now is something that I already know there's a bug. All right, so I remember testing in a baseline, moving up to more industrial scale code because it's a small project. But that's what you're trying to get after. And that's where you expand with LLVM passes. I should say one thing, I'm not particularly interested in something that defines a bug right from the static analysis. I'm not concerned about that. I'm trying to get hints. I don't care, I don't want one solution. That's great if I get it. I don't need that. I want to get a hint to understand how code is being developed, where possible bugs might be. If they're exploitable bugs, that's what needs to be stopped. Call function graph. I mean, this is basically the mapping, how we map our source to the dynamic. The dynamic analysis has to be done. In the hacking community, static analysis is great, but generally speaking, it's frowned upon in terms of really going after somebody. If you're in the wild, you're looking at somebody else's code, you might not have their access to their source. So if you're going to do it, you can do black box testing. Okay. Function graph, you want to map to the static and dynamic. That gives you that mapping in terms of what you want to try and hit from the black box perspective, even though you're really white box testing. Data dependency, this is where I'm parsing using a lot of the libclang tools, trying to get local variables, where they resolve to, what their types are, and really understand the dependency chain. Okay? When I get back to the dynamic, you're going to see LLDB, the basic question I want to answer is, why did this crash? Where did it come from? Doing a taint analysis, all that kind of stuff that security professionals want to do. That comes from, that information can be augmented using Clang. I can get in there, I can look at the dependencies, I can start to figure out where things came from, what the types are, maybe where things are being read to, overwrite if I need to. It's just fine. The hypothesis engine, this took a little bit of searching, but eventually I settled on Pike. It's a Python module. open source, and it's a lot like Prolog. I'll talk about it in more detail, but I want something relatively simple, relatively lightweight, could be augmented later if need be, but gives me a lot of flexibility. And one of the big things I want to do is add as I go, iterative. I want to be able to take something, run it, get a few hints, add to it. And as I go along, keep adding rules, keep adding facts, keep adding knowledge. That's the goal. A fuzzer, generic dynamic instrumentation is what you're really looking for, okay? So guys from Intel, PIN is something I really like using. It's really nice. For this one, I'm going to step back, just use something that's simple fuzzer. That's fine. That satisfies my requirements. Okay, I just want to be able to grab the registry states, be able to get information back in terms of why did it crash, where did it crash, what are the key components of what was going on at that time. So as we start looking in a little more detail, yes, it was not exactly fun to rewrite 1,400 lines of Perl to Python. It had to be done, that's fine. And it's just one of those situations where it now allows me a little more control of individual functionality. So I want to go back and run part of it, something, grab specific outputs, create it in a different format. I have that flexibility. Not a painful thing to do, not exactly a fun thing to do either, though. It just makes it a little more comprehensive. One of the other things eventually I'd like to go to right now, in the project is be able to run custom checkers, extensible. You want to be able to write checkers for your development environment, for your product, for your environment, with other colleagues, learn from each other, share things. That's where LLVM has a great amount of leverage, and it's where you can learn a lot from your code and from your colleagues. Again, you want to catch that exploit before it goes out the door. So, call function graph, I mean, this just is an anchor. You get this for free with LLVM, and it's nice. We really want to develop hypotheses in terms of what these functions do, how we can influence things to get to an exploitable point. I mean, the goal of the tool chain in this sense is find something that's exploitable. I can do that with a call function graph to try and limit where my choices are, where the inputs are coming from, do dynamic disassembly if I need to with LLDB or something like that, see a standard in, standard out, file reads, all that kind of stuff. That's something I really wanted to tie in, okay? Get into a hypothesis. It's a development tool, we want to learn from something. Okay, the other thing about I like about this in terms of being able to communicate where code is going. I mean, when I talk to a lot of guys, we talk on the phone, talk on chats or something like that. By the time we wrote our 2 different versions of code, yeah, they kind of do the same thing, but they do it very differently sometimes. And you want to be able to communicate a goal. So call function maps, this stuff is actually created in the Pike syntax, which looks a lot like Prolog for anyone who's done that before. Prolog is not a fun language for me to program, at least in, but it's useful. So in this one, you've seen just basically a small set of inputs and all the rest. Grabbing functions, grabbing what the types are, grabbing the function names, seeing what's actually used in subfunctions and calls and all the rest. And it gives you that real layered, finely layered map in terms of where things are going, allowing you to do a taint analysis right from the start if you want. Data dependency, this is all stuff just parsing it. I mean, this really ends up being about 100, 200 lines of Python code for me to parse everything and start putting this into facts and reuse this for any kind of interpretation downstream. And I link that to the call function graph, and I know how things are being called nicely, get the exact arguments and all the rest. One of the things about this is I can read and write to memory if I need to force a circumstance. So for different targets, maybe the exploitation is kind of different. Well, I got LLDB, I can do memory read, memory write, throw it right in there, see what happens. Maybe it's a corner case. Maybe we can't quite simulate the input. That's something that's important. We can get there with simple execution. The hypothesis, again, this is Pike. So we ought to have a goal for what we're doing. Incorrect assumptions, this is what I was basically hinting as. People assume different things that leads to some projects, some problems in terms of where the project is heading. When you back things out and put it into an AI engine, you get some of these facts and all the rest, but you also get assumptions that are built into the facts. And that kind of leads to some interesting information. That's probably something I'll have to look at that's been a bit of a tangent on the project, but I found it very interesting in terms of if you have different files and all the rest, you can see where things are common and where things are uncommon, and it presents some interesting information. So Pike, this is written by Python, written in the Python community, a guy from Bruce Atkinson in Florida. Great fact storage, draws conclusions, you can prove plans. Plans are one of the nice features about this, and for folks who don't know, it uses partial functions. It's basically the defined function with some variables all built in. And you do that with a little bit of recursion, and I have a really nice set of circumstances that are going to just keep on, and I can keep iterating over and adding depth to. So in other words, I start at the top level function, I set a set argument, I can call that, go into recursion on that to a secondary argument, keep going, and I have a nice line down a tree as to where things are going. And I can iterate on that and keep fuzzing on that. If you want to grab memory, you want to grab other things along those lines, you can do it. It's not too hard to do. And it gives you a lot of flexibility, and it's built into the project as it goes. I think that's about on that one. Now the conclusions, this is actually an important point. In terms of the facts, like I said, I really want something iterative. Pike recompiles the facts every time if you call it. We have basically a concept of a knowledge engine. As you have the knowledge engine, you want to recompile, you want to assemble the facts again, you can do that. It's relatively simple and straightforward. The situation that I've always encountered is, I want to do my analysis, I want to run a fuzzer on it, and as soon as that comes out, from that end result, I want to assemble what crashed, what didn't crash, what the circumstances were, where I thought the variables were, and that gives me a hypothesis as to what I should run again. If I have my second set of things, I rerun again, it's iterative, it goes along. This is not something that's going to run fast. This is something you do over lunch, do overnight. This is like the old adage, instead of speed, quality, and price, this is speed, quality, and security. Pick two, you know. Dynamic instrumentation. Right now, this is just a fuzzer. I am incorporating Sully, which is a well-known fuzzing package. Uses a different debugger, but you could replace it with LLDB. And it's not too hard to do that, actually. There are about 51 files in Sully, Python files, and only about 3 really pertain to the debugger. Okay? Sully has really good input generation, so why rewrite that again? It's another advantage of taking for Python, another advantage of using what's already existing in the community. You can use what you have, take what people are familiar with, incorporate that into your toolbox. In the end, you want to use what people are using to break your software. So if you have something out there in the wild that's very successful, like Sully, you know, incorporate it into your development environment. Try and learn from it what they're using to try and target. Exploitation techniques can also be delivered. There are ROP payload generators in Python. There are memory heap sprays, that kind of stuff. You can do these kind of things. So you can simulate a lot of the things, and you don't have to drop down to C++, and you can pass along relatively small files that are meaningful. Crash investigation. I mean, this was LLDB right away from the start. This is a good thing, because I can script what I want to grab and then augment it with the facts. I have my facts, I have variables I want to grab. I grab register states, what the states of the variables are, query those things, put those into the next case. Okay. One thing I should probably add about this is, in terms of, you know, register states is nice, but there are more additional things that we want to add into LLDB that are not quite in there that are satisfactory for looking at different architectures and things like that, nuances that we might want to add later on. It's a little bit lacking in some of those, but here's a register dump. Easily grab that information and start mapping it to what variables are in the subfunctions and that kind of thing. And you can make a diagnosis based on who has, you know, what registers could be controlled from what variables, system libraries, all that kind of stuff we can map in. So, and that's pretty typical stuff that a hacker is going to do. So, tracking local states. At this point in time, you know, we want to be able to grab states. One of the difficulties with working with these things is, you know, I'm basically automating breakpoints and grabbing states and that kind of thing to figure out where I want to be and what is relevant. And that's part of my facts. I don't want to take forever and do a breakpoint every single function call, that kind of thing, but I want to grab key parts. This is something that's going to have to be improved for the community, but for now, this is sufficient. You know, I should point out, most of the programs, again, have been relatively small where I know the issues, but even when I'm asking for friends, you know, you mind sending me some code that you're not particularly proud of, but you're willing for me to break, you know, it works fairly well. So, but this will have to be augmented for industrial sizes. I'm bringing up, working for DARPA and demonstration, we're going to work on V8. Well, it's a pretty significant code base, not huge, but, you know, significant. And in that sense, you need to get a little more information, get a little more functionality to improve speed and performance, make it a little more usable to get information out of it. All right, so coupling, one of the things you have to do in terms of being integrated is get the dynamic results, feed it back to static, and map it back to source code. I mean, just getting a crash is nice, and if you're recording the crash, that's a good thing with something like Sully, but you really want to point it back to, at this line, you had an integer overflow, or you had a buffer overflow, and it mapped down to here, which allowed me to deliver a payload, and that gave me arbitrary code execution. Okay, so we need to do the coupling. That's where the AI is key. Pike so far has been sufficient in terms of relatively minor issues, being able to deduce how do we draw those out and hint them back to specific variables at functions that were corrupted by an input that weren't checked, that you can kind of deduct relatively quickly. And that's, of course, nice when you're doing debugging. But there's going to have to be a little bit more for industrial scale. This is a place where the community can probably get involved. This code will all be open sourced, and something that we'll probably augment in the near future for the demonstration case and deliver it out there. This is another place where I think checkers could help, doing the static analysis and allowing building of checkers at a relatively easy scale for other people to share. You know, that kind of collegial feel gives you the ways to find more and sweep through your code and be able to personalize it in terms of what you're doing. So this was actually one of the alpha things. I mean, you can draw, this whole script was about 20 lines of code after you've done a whole bunch of sub-functions and all the rest. But you basically are doing a scan build, map out the source, get an artificial intelligence, build up the knowledge engine, do some fuzzing, do some summarization of why things crashed, what worked, what didn't work, get a whole bunch of case files, and then you can start doing the analysis and start it over. So this was a very simple driver function that you can do in 15 lines of Python code. Okay. Now, there's a lot under the hood in terms of the fuzzing. Now, again, there was automated breakpoints put in there, breakpoints put in functions of interest, looking at variables, capturing states of variables at different times. The summarization is very, right now it's very trivial. That's a place where things are going to have to improve. But it gave you feedback in terms of, okay, automated, I can walk away half hour, 45 minutes later, and actually get a feel for where things are probably weak. Plugins, again, this is getting back to selling other things. Python's used a heavily amount. Ruby and Python are both heavily used scripting libraries for hacking in the hacking community. Very easy to use. You can get 20 lines of code and start fuzzing things and all the rest. There have been presentations at DEF CON, Black Hat, for anybody who's interested, how to build an army of fuzzers with monkeys and stuff like that. Entertaining presentations. So LLDB could be replaced. These are basically the three functions you can see here, the substantial change that are necessary. It's only 3 out of 51 files. So yeah, these are actually fairly substantially used because a debugger is obviously a large part of a fuzzer, but it's really only a minor part of the code base. Most of it is meant for the other auxiliary functions of fuzzing, made it to logging, tracing, generating inputs, being able to link all that together. This could be incorporated, and this is part of something that we will do or start to address inside of our project, but we probably won't finish it for our deadlines back to DARPA. So one of the things we absolutely have to do in terms of this is keeping it modular, general architecture that's very easy to customize. I mean, this is a situation where I've worked with a lot of different hackers and all the rest. You have to throw Python code back and forth at each other. You have to be able to look at things and be able to fit it back in. The architecture that LLVM that we're borrowing from this in this case is static analysis, which we get the call functions. We can get all these kind of things and get a starting ground for free. Now we need AI linkage to be able to deduce things. How we interpret those results is really kind of the art of where this needs to go. That's something that can be played around with as a community, as with different people, different individuals, different projects. It's not a one-size-fits-all, in my opinion. I think different people are going to have different needs for whatever their purpose is, whatever the product is. But plug and play is necessary. You have to be able to get that. Long-term viability kind of resides on getting people involved, seeing what works, what doesn't work, and finding the general patterns. So in terms of a workflow, right now this is basically just me and a couple of guys who every once in a while check it out. But if you get this large enough, right, static analysis, you can leave it as a scripting. I mean, the calls are there, basically just a rewrite, and we can handle things quite nicely. The function graph, we're storing as JSON. You can store it to SQLite. You can do all these different things. Ideally, in my view, you'd like to see this as a server architecture, as a service, where people could call on things, look at a call function graph, look at their call function graph. I mean, you could do this on versioning, because you want to be able to look at different versions of code, how the bug was introduced, what practices were not followed, or whatever happens. I mean, these things happen. We all have bad days of coding. It's all right. We just know how to fix it. The translation of facts and all the rest, that's actually relatively straightforward, and we can keep that as JSON, SQL, any kind of format will really do. It's really a presentation of those facts that's important. That's something that, it depends. If you get used to Pike, then the looking at the facts is relatively straightforward. You see things that pop out at you. This looks very much as you might expect in terms of variable of a function is this. Type of that variable is this. Children of this, arguments of function, and it's just a long list. You can try and present it in every different ways. You can try and present components of it, and I think that's probably where things are going to go. The fuzzer uses those facts and then puts out more hypotheses in terms of what are we going to assume, what are we going to try and prove, and that kind of thing. Right now, those are pretty much driven in terms of what the program is going to do. I basically put in categories in terms of this program is reading from files, this program is going onto a server, this program is logging here. Put in a category in terms of what I expect problems could be, where the problems could be. Try and draw out the issues that I might see and try and improve it. One of the other things that's important in terms of going further, in terms of what else can be done, the Blackbox techniques have to be kind of incorporated in this. One of the things that's been interesting about working on this project is the amount of feedback I get from other guys who are basically like static analysis, come on. But static analysis is really important, and you have to map it back to where the problem comes in. DARPA was interested in this project because you are able to take something from source code and put it out into the field and try and map it back and forth. You want to be able to iterate. Okay? The LLVM interpreter, to be able to interpret and simulate different architectures is really important because the exploitation techniques are different for different architectures. You have different size, all kinds of environment variables that have to be handled a little bit differently for exploitation. Something that might be exploitable here may not be otherwise. Scripting language, this is something I'm a big believer in now. I think that there are other things, opportunities to put this back and forth. Of course, with LLVM, you can port from Python back to C++ relatively easily. All right, so the timeline for this, we have already delivered an alpha. DARPA was really happy. This will end at roughly the end of the month. At the end of the month, this will start to be vetted with DARPA and all the rest, and they will present it, and they will be either happy or they will be, we want a little bit more done. At that point in December, maybe probably mid or end of December, this is something we can open source. We'll probably put up on GitHub, probably put up little demonstrations, try and get people excited about what we're doing, and also pass along some of the hacker conferences and that kind of thing. See what people feel, see what people want to do. You're welcome to contact me. I can answer questions anecdotally. I can't give out source code just yet because I'm still under contract. There's a lot of work to be done here, but there's a lot of interesting things. I have to thank some people here. A lot of these guys are from MITRE. If you guys don't know them, these are some nice guys. Peter Zacko from DARPA, Bit Systems is a liaison there. Al Spitz, so these guys are from from MITRE. And thank you very much for having me. It's been a pleasure to be here. So, questions?
Well, time for a few questions.
Hello, John Criswell from University of Illinois. So if I understand correctly, you're essentially building a system that basically detects crashes and then, through fuzzing and such, and then tries to map that back to the source code to isolate where the error is occurring, correct?
Yep.
Okay. Have you considered using some of the facilities that are available for LLVM, such as address sanitizer, the integer overflow checker, safe code, softbound, et cetera, yep, to find errors in some of these runs?
Yeah, you can use those and it will point out errors. Other times you put in specific errors and you will not find issues with static analysis.
No, these are dynamic analyses.
Oh, sorry, yeah. I've used tools. I haven't done much on the dynamic side with Clang. I've used mostly LLDB stuff for actually doing the fuzzing and all the rest. I haven't done much there in terms of, I've mostly used static analysis tools, and I'll incorporate later on.
Okay,
yep.
Thank you.
Yep.
Any more questions? Okay, let's thank the speaker again.
All right.